What would happen if you fell into a black hole? If you'd asked Albert Einstein, he would have told you that according to his general theory of relativity, you'd be sucked into the black hole's singularity, the point where space-time curves steeply inward and all the laws of physics seem to break down. After that, nothing can escape. In the 1970s, Stephen Hawking took a semi-classical approach to black holes. Bringing together quantum theory and Einstein's relativity, he proved that black holes emit a small amount of heat that eventually causes the black hole to evaporate. Still, according to Hawking, if you fell into a black hole, you and your particles would be lost to the universe forever. This is Don Page. He was a postdoc with Stephen Hawking, where they became friends, despite the fact that they ultimately landed on either side of one of the most controversial debates in modern physics.
I looked at Hawking's argument and I became not convinced by it.
Hawking's work implied that black holes violated a central principle of quantum mechanics, called unitarity, which says that the present always preserves information about the past. So how could it be possible that black holes destroy information? This became known as the black hole information paradox, and for decades, it made physicists queasy. According to Page, if you were to fall into a black hole, you wouldn't be gone for good. Particle by particle, the information needed to reconstitute your body would reemerge.
Well, it would be highly scrambled by the black hole. It'd be much worse than even, if you just cremated the body and it turned into smoke and ashes. But, another analogy is if you burn up a book and you have all the ashes, the information is still somewhere there, somewhere in the universe, we believe.
The key to understanding why the information is preserved lies in a process called quantum entanglement. When black holes emit radiation, that radiation maintains a quantum mechanical link to its place of origin. If you tried to measure the radiation or the black hole separately, the information would look random. But when you look at them together, they exhibit a pattern.
If somebody took a coin and cut it in half, and then you sort of shook it up and put it in two envelopes and sent it off to two people, then of course there would be what we call correlations in it. If one person gets a head, the other person would have tails. And this quantum entanglement is like that, except it's an even more subtle.
This is the Page curve, which he created to track changes in the entanglement between a black hole and its radiation as it ages. The degree to which the information is entangled is called its entanglement entropy. At the start of a black hole's life, its entanglement entropy is 0, since it hasn't emitted any radiation. And at the end, its entanglement entropy is 0 again, since the black hole has evaporated. But in between, as radiation trickles out, the entanglement entropy grows. Page showed that, in theory, information can escape from a black hole. In a series of groundbreaking papers, physicists have shown that the entanglement entropy of black holes really does follow the Page curve.
These calculations give more evidence that indeed the information does come out, but the details of how that actually happens and still remain to be understood. And it raises the picture that maybe space-time itself is not fundamental. Maybe there's something deeper than space-time, and maybe the basic quantum description will involve something that's not space and time. So I think there'll be parts of the puzzle, I think, that'll persist for many more decades.
Another puzzle that's baffled the scientific community for decades is superconductivity. When various solids are cooled to extremely low temperatures, they can conduct electricity without losing energy. This happens because the freezing temperature allows electrons to move slowly enough to overcome their natural repulsion with each other, and they begin to form pairs. Like any good couple should, they balance each other out and begin to move in the same direction. When this happens, electrical resistance disappears. This is what makes superconductivity the holy grail of energy efficiency, if only scientists could overcome the limitations of temperature. This is Ranga Dias. This year, he and a team at the University of Rochester created a metallic compound that for the first time exhibited superconductivity at room temperature.
So you have a very small two diamond tips that's sitting opposite to each other, and then you put your sample that you need to study in between those diamond tips. So you can apply force mechanically.
Dias's team applied pressures almost as extreme as those found at the Earth's core. They did this by crushing the compound inside a microscopic niche they carved out of a diamond anvil. Then, they triggered chemical reactions with a laser beam.
So that way, we were able to really find a room temperature superconductor. It's under pressure, right? What we have found is under pressure. So somebody can argue that, okay, so you went from one extreme to another extreme. So who cares? Or, what's a big deal in that sense, right? But I think there was a time that we were, even the scientists were thinking that room temperature superconductivity is not possible. To be honest, the very first time when we saw this one, I didn't really believe it. And I was like, okay, this is too good to be true. And why we are seeing this nice resistance. Everybody around the world contact me via email or phone calls, and they were very excited, and this is a landmark discovery. But there are a lot of work to be done because even though we know the initial composition, what are the material that we put together to pressurize it, but we don't know actually what it is really, what the sample is superconducting. So that those studies need to be done.
So for now, levitating trains, lossless power transmission, and perfect energy storage are still utopian dreams. But Dias believes they're not far off.
I would say I'm very optimistic. Probably in the next 5 years or 10 years, may be able to get to a real application.
In 2006, an astronomer detected a brief and extremely powerful radio signal coming from a distant galaxy. Over the next few years, dozens more were observed. Astronomers traded wild theories trying to explain them. This year, a fast radio burst was observed again, but this time it came within our own galaxy. In just a millisecond, the source emitted 100 million times more power than the sun. Brian Metzger and his colleagues at Columbia University analyzed the data and found the source, a magnetar.
So a magnetar is a neutron star. So neutron stars form when massive stars die at the end of their lives. The core of the star collapses in and forms a neutron star, a very compact object about the mass of our sun, but the size of New York City. And then the outer layers of the star explode as a supernova. And so a neutron star is what's left over. And magnetar is an extreme version of a neutron star with a very strong magnetic field. So there was a magnetar in our own galaxy that produced a flare of X-rays, and arriving on Earth at essentially the same time as the X-rays was a burst of radio emission, which if we'd put it into a different distant galaxy would have looked a lot like a fast radio burst. But we were, identifying that it came from a magnetar within our own galaxy. So that's pretty good circumstantial evidence, that magnetars can produce fast radio bursts. Fast radio bursts are great because we can see them almost to the edge of the universe. And so in addition to actually understanding what's producing them, one of the exciting things is we can use them as probes of the state of matter between us and the radio source. And so I think that's very exciting as we discover more and more fast radio bursts. And if it turns out that they come from magnetars, then we're also probing where all the magnetars are in the whole universe, which is something we didn't think, would have ever been possible.